Hey folks, my name is Dima. I'm a senior web developer based in Berlin. I've got more than 8 years of experience across different companies. On this channel, we talk about passing front-end interviews and advanced front-end topics in general. If you are preparing to an interview or working on your career as a web developer, you will find some really good stuff here. Today, I want to discuss WebTransport, a relatively new web technology that's getting more attention lately. When developers hear about WebTransport, the first question is usually, does this replace WebSockets, or should they work together? The answer isn't straightforward, and many developers are confused about when to use what. In this video, we will explore how WebTransports work under the hood, its pros and cons, and the specific use cases where we should use it. We'll also compare it with WebSockets, so you can make informed decision in your project. Let's dive in. The main question we're discussing today is WebTransport a substitution for WebSockets or not? And like many things in tech, the answer is it depends. It's not simple replacement, it's more like a specialized tool for specific scenarios. The short answer is that WebTransport doesn't replace WebSockets universally. Instead, it solves specific problems that WebSockets have struggled with, particularly around head-of-line blocking and mixed reliability requirements. Think of it as adding a new tool to your toolkit rather than throwing away the old one. Today, we will explore the evolution of real-time web communication technologies and how they compare. We'll start by understanding WebTransport's capabilities and how this new protocol changes the game for real-time communication. Then, we will dive deep into comparing it with established WebSockets. Looking at the strengths and limitations of the current standard, we'll examine the technical differences under the hood, from TCP versus QUIC to head-of-line blocking to connection establishments. Then we will deep dive into comparing with established WebSockets. Looking at the strengths and limitations of the current standard, we'll examine the technical differences under the hood. Finally, we'll discuss when to choose each technology with specific use cases and provide real-world implementation considerations with practical guidance for development teams. By the end of this video, you will have a clear framework for deciding between these technologies. First, let me give you the key takeaway upfront. WebTransport is a new web communication protocol built on HTTP3, which uses QUIC under the hood, but the key benefits are substantial. First, you get multiplexed streams that prevent head-of-line blocking issues. This is huge for applications that send different types of data simultaneously. Second, there is optional unreliable data delivery for better latency. You can choose whether each message needs guaranteed delivery or not. Third, it's built on modern QUIC infrastructure, which means faster connection establishment and better network efficiency. And fourth, it maintains bidirectional messaging, just like WebSockets. Think of it this way. WebTransport gives you the best of both worlds. This flexibility is what makes it powerful for specific use cases. Regarding the browser support, as of August 2025, WebTransport has limited availability across major browsers. Chrome, Edge, and Firefox support it, but Safari doesn't. This shows about 79% global coverage, but that missing Safari support is significant. This means you can't rely on WebTransport alone for production applications yet. This is actually a crucial consideration for adoption. You need to plan for fallback strategies. The good news is that the specification is stable and browser vendors are committed to implementation. But for now, it's best suited for applications where you can control the browser environment or if you can implement graceful fallbacks. Let's start with what we already know, WebSockets. WebSockets become popular because they solve the real problem that existed in web development. Before WebSockets, we had polling and server-sent events, but both had limitations. Polling was inefficient because you had to constantly asking for new data, it took a lot of resources, and also there was a polling delay. Server-sent events were unidirectional. Only the server could push data to the client. WebSockets gives us bidirectional communication with much lower overhead, since there are no HTTP headers after the initial handshake. You get real-time delivery with no polling delays and a persistent connection that eliminates the cost of constantly reconnecting. Some important facts about WebSockets. They were standardized back in 2011, making them over 14 years old now. They use a persistent full duplex TCP connection and they power most of the chat apps, live feeds, and collaborative tools we use today. WebSockets have real limitations that become problematic in certain scenarios. Let me explain the three main issues. The biggest issue is head-of-line blocking. Since WebSockets use a single-order stream, when a packet is lost in the network, all following messages get blocked until the packet is retransmitted. This might not seem like a big deal for a chat application, but it's a problem for interactive applications like games and trading apps where timing matters. Imagine you are playing an online game, and because one packet containing your teammate's position got lost, your own movement commands get delayed. Second, there is a single stream per connection limitation. WebSockets have no native multiplexing capabilities, which means if you are sending different types of data, for example, chat messages and files, a large file upload can clog the pipe for quick chat messages. Developers often have to work around this by opening multiple WebSocket connections or building custom multiplexing solutions on top, which adds complexity. Third, there are reliability constraints. WebSockets always ensure reliable order delivery, which sounds good in theory, but it's actually inefficient for certain types of data. For live video streaming or real-time game, the latest data matters more than all data. If a video frame from 100 milliseconds ago gets lost, you don't want to wait for it or to be retransmitted. You would rather skip it and show the current frame. But WebSockets don't give you that choice. There is no built-in unreliable messaging option. To understand why these limitations matter and how we got here, let's look at the evolution of web protocols. Back in the HTTP 1.1 days, each HTTP request needed a separate TCP connection. This was very resource-intensive for several reasons. Managing multiple TCP connections was inefficient. Servers had to maintain many simultaneous connections, eating up memory and file descriptions. Each connection required a separate TCP handshake plus TLS handshake, adding significant latency, especially on mobile networks or long-distance connections. But here's the interesting and somewhat ironic part. We actually didn't have a head-of-line blocking problem in HTTP 1.1 because we had multiple HTTP connections. If one connection got stuck waiting for a lost packet, the other connections could continue independently. It was look like having multiple roads on a highway. If one road had an accident, traffic could still flow in the other roads. So while HTTP 1.1 was inefficient in terms of resource usage, it accidentally solved the head-of-line blocking problem. This is important to understand because it shows us that the solution to head-of-line blocking problem could be about maintaining independence between different data streams. HTTP 2 tried to solve the efficiency problem with multiplexing. The idea was really cool. Instead of opening multiple TCP connections, let's make all HTTP requests share one TCP connection. This is much better for performance because you remove the overhead of multiple connection establishments. It is also better for server efficiency, since servers need to manage fewer connections per client. But these optimizations create a new problem: TCP head-of-line blocking problem. Now, when a packet is lost at the TCP level, it blocks all streams because they are all sharing that single TCP connection. It's like we went from multiple highway roads back to a single road. More efficient in theory, but if there is an accident, everything stops. There is also no unreliable delivery option in TCP. All data must be delivered reliably because that's how TCP works. TCP doesn't give you a choice. It will keep retransmitting lost packets until they arrive, even if your application would prefer to just move on to newer data. HTTP 2 is more efficient than HTTP 1, but for certain types of real-time applications, that efficiency comes at the cost of performance when network conditions aren't perfect. Now let's dive deeper into why this is such a fundamental problem. When network congestions occurs, applications must reduce data transmission to prevent network collapse. If everyone keeps sending at full speed during congestion, the network becomes unusable for everyone. For many applications, this creates a critical dilemma that doesn't have a good solution with TCP. The obvious solution seems to be reducing encoder bitrate when you detect congestion, but this approach has several serious problems. First, it only affects future frames. Those already encoded frames are still sitting in the queue and will be sent, so you don't get immediate speed improvements. Second, it's an all-or-nothing approach. If one viewer has a slow connection, you might end up reducing quality for everyone else too, which is not ideal. Third, it's expensive because encoding separate streams per viewer at different bit rates is costly for most applications. And fourth, there is a latency impact. The time it takes to re-encode at a different bitrate adds delay when speed is critical. So we're stuck at this point. We can't really fix this problem at the application layer because the transport layer, TCP, is making decisions that don't align with what our application might need. This is where the fundamental mismatch becomes clear. TCP was designed for reliable file transfer, not real-time meta streaming. Let me show you what happens in practice. You have a server with encoded messages sitting in a queue, ready to be sent to the client, but then network congestion happens. One message can't be delivered because the network is overloaded. What can we do? We must reduce data transmission to prevent network collapse. But here's the problem. Those messages in the queue are already encoded. We cannot reduce them or modify them. There are binary data ready to go out the door. The only thing we can do is reduce the size of future messages that haven't been encoded yet. But that doesn't help with current backlog. And with TCP, if the congestion persists, the only solution is to drop the entire connection. All data that already in the queue is lost and the application must restart from scratch. This is clearly not ideal for real-time applications where some data loss is acceptable, but connection drops are bad for user experience. You would much rather lose some frames than have to reestablish the entire session. This brings us to the fundamental problem of reliable delivery. For real-time applications, all data is often not just useless, it can actually be harmful. For example, in gaming, if you receive a player's position from 200 milliseconds ago, it makes them stuck on screen, which creates a confusing experience. The newer position data that arrived later is much more valuable than the old position that got delayed. For live video streaming, retransmitting a lost video frame causes stuttering. Users would much prefer to see a brief glitch or skip rather than have to video freeze while waiting the old frames to be retransmitted. Let me show you a concrete example of why head-of-line blocking is such a serious problem in financial applications. Here we have Apple stock, showing $118.30 with a 2.1% gain. But here's the issue, this price is actually outdated. The current price is $124.11, which is almost 5% higher than what user is seeing. Look at what's happening in the WebSocket connection. We have a sequence of price updates, but that 119.35 message got stuck, maybe due to network congestion or a lost packet. Because WebSockets must deliver every message in order, that stuck message is blocking all the newer price updates from reaching the client. So the trader is seeing the old price and thinking about making a purchase decision based on that price. But the reality is that the stock has already moved significantly higher. This isn't just a technical problem. It's a business problem that could cost real money. This is exactly why unreliable delivery becomes valuable for certain types of data. This is where HTTP3 with QUIC comes in to solve these fundamental problems. QUIC is essentially a complete redesign of how we do network transport. The biggest improvement is that there is no head-of-line blocking because a lost packet in one stream doesn't block other streams. QUIC manages multiple independent streams within a single connection. So if stream 1 has packet loss, streams 2 and 3 continue flowing normally. You can mix reliable streams with unreliable datagrams in one connection. So you get to choose per message whether you want TCP-like reliability or UDP-like speed. Critical data like user identification can use reliable streams, while real-time data like mouse movements can use unreliable datagrams. QUIC also has much faster connection setup, 0 to 1 round trip versus 2 to 3 round trips for TCP plus TLS. QUIC combines the transport and security layers, so you establish both the connection and the encryption in a single step. You also get transparent network migration, like switching from Wi-Fi to LTE without dropping the connection. QUIC connections are identified by connections IDs rather than IP addresses, so they survive network changes. But there are important limitations to be aware of. Safari doesn't support it yet, which limits adoption. UDP port 443 and QUIC traffic can be blocked by many enterprise and campus networks that have aggressive firewall rules. There is infrastructure immaturity since many common reverse proxies and CDNs still don't fully support WebTransport. And importantly, there is no peer-to-peer or NIT traversal capability. It's strictly browser-to-browser communication, unlike WebRTC, for example. Let me show you the difference in connection setup times. With HTTP over TCP plus TLS, you need to go through multiple steps. First, there is a three-way TCP handshake. Then TLS needs to create a secure tunnel with its own handshake process. Finally, you can upgrade to WebSocket with another round trip. That's multiple round trips before you can start sending application data. Compare this to HTTP3 over QUIC. The three-way handshake includes TLS encryption setup, so you get both connection establishment and security negotiation in the same round trips. Then you can upgrade to WebTransport. The total time is significantly shorter. This difference becomes really noticeable on high latency connections like mobile networks or international connections. If you have 100 milliseconds round-trip time, the difference between 3 round trips and 1 round trip is 200 milliseconds of additional latency before your application can even start working. For real-time applications, that's significant improvement in user experience. WebSocket connections use one bidirectional message channel. Everything goes through this single pipe. If one message fails and need to be retransmitted, all messages that come after it get delayed. The red X shows a failed message, and you can see how it blocks everything behind it. WebTransport takes a completely different approach. It uses the same UDP connection for both streams and datagrams, but they are logically separate. You can have multiple streams for reliable, ordered, higher latency data. This is like WebSockets, but without the head-of-line blocking between different streams. And at the same time, you can have datagrams APIs for fast and reliable, low latency data. This is like UDP, but within the secure WebTransport connection. When one message fails in a stream, as it's shown by the red cross, only that specific stream is affected. Other streams and all datagrams continue flowing normally. This architectural difference is what enables applications to have both low latency updates for real-time data and reliable delivery for critical data, all in the same connection. WebTransport operates over HTTP3 and QUIC to provide a secure, low-latency channel with advanced capabilities. The core innovation combines UDP-like and reliable messaging with TCP-like reliable streams, all multiplexed on a single connection. You get security because it's always secured. HTTPS is required. You get performance with faster handshake than TCP plus TLS. And you got efficiency with the right balance between speed and reliability, letting you choose the appropriate delivery method for each type of data. Multiple independent data streams per connection where different data types use separate logical channels and one stream's delay doesn't block others. You get flexible delivery options with unreliable datagrams for time-sensitive data and reliable streams for critical messages. The developer gets to choose per data streams what's more appropriate. There is reduced overhead with QUIC, 0 or 1 round-trip handshake, and lightweight stream creation versus creating new TCP connection. One really cool feature I mentioned before is connection migration, and this solves a real problem of mobile users. With WebSockets connection, when you switch from Wi-Fi to LTE, which happens time to time as you move around, the connection needs to be completely reestablished because TCP connections are fundamentally bound to IP addresses. When your IP address changes, TCP considers it as a completely different connection and drops the old one. WebTransport with QUIC connection use connection IDs instead of IP addresses as the primary identifier. So when you switch network and get a new IP address, the WebTransport connection automatically reconnects to the server using the new IP, but maintains the same connection ID. This migration is seamless for user and invisible to the application. This is especially valuable for mobile applications or any application where a user might move between networks. Think about a video call that continues uninterrupted as you walk from your office Wi-Fi to the cellular network in the parking lot, or a game that doesn't disconnect when you switch from Wi-Fi to mobile data. Let's look at some real-world examples. High-frequency trading platforms are a perfect example. In these systems, market data feeds should use unreliable datagrams because the latest price is more important than an old price. If you're getting price updates like 100 times per second, missing one update is fine, but getting them out of order or delayed is not good. Order confirmations, on the other hand, should use reliable streams because every trade confirmation is absolutely critical. You cannot lose a "your order was executed" message or something like that. Portfolio updates also use reliable streams because account balance changes must be completely accurate. WebTransport wins here because WebSocket head-of-line blocking could literally cost trades money when price data gets delayed behind other messages. Cloud gaming platforms like Google Stadia or GeForce Now are another great example where WebTransport should work well. With WebTransport, you could handle everything in one connection. Video frames were unreliable datagrams, player input were reliable streams, and game state events also were reliable streams. This unified approach could simplify the architecture while maintaining the performance benefits of both unreliable video delivery and reliable input state management. Real-time collaborative design tools like Figma illustrate another pattern. Cursor movements should use unreliable datagrams, since new ones are coming constantly. Document changes, however, should use reliable streams, because every edit, text change, or design modification must be preserved. Losing document changes would be really bad for collaborative tools. But let's be clear, WebSockets aren't going away, and there are many scenarios where they are still the right choice. Use WebSockets for simple real-time messaging applications like chat systems, notifications, and live updates, where you're essentially sending one type of data and the complexity of WebTransport isn't needed. If you're building a basic chat app or a simple live dashboard, WebSockets are perfect and much easier to implement. When universal browser support is required, including Safari and older browsers, WebSockets are your only option right now. If you're building a consumer-facing application that needs to work everywhere, you can't rely on WebTransport yet. For a single data type communication where all messages have the same priority and type, WebSockets work great. If everything in your application has the same delivery requirements, all reliable or all real-time, then you don't need WebTransport flexibility. When reliable delivery is essential and every message must arrive in order, WebSocket's guarantee of reliable order delivery is actually a feature, not a limitation. For applications like financial transactions or any system where data loss is not acceptable, WebSocket's TCP foundation is exactly what you want. And when you want easy implementation with major libraries and extensive community knowledge, WebSockets have a huge advantage. There are robust WebSocket libraries for every programming language, good documentation, and community knowledge about best practices. Use WebRTC when you need peer-to-peer communication, direct browser-to-browser connections without going through a server, for real-time audio or video calling, file sharing where you want to avoid server bandwidth costs, or conferencing applications with video calls and screen sharing. WebRTC fills a different niche that neither WebSockets nor WebTransport can address. In practice, you will want a graceful fallback strategy because the reality is that you need to support all browsers and network conditions. The ideal approach is progressive enhancement. Start with WebTransport for supported browsers, where you can take advantage of its advanced features. But when Safari doesn't support it, or when corporate networks block quick traffic, gracefully downgrade to WebSockets. If even WebSockets don't work because you are dealing with very old browsers or very restrictive corporate networks that blocks WebSocket connections, you can fall back to server-sent events or polling for basic real-time functionality. This layered approach ensures your applications work everywhere while taking advantage of the best technology available in each environment. It's more complex to implement, but it gives you the best possible user experience across all scenarios. The key is designing your application architecture so that the transport layer is abstracted. Your application logic shouldn't need to know whether it's using WebTransport datagrams or WebSocket messages. It should just send real-time position update and let the transport layer figure out the best way to deliver it. There are some important considerations to be aware of when implementing WebTransport because the flexibility comes with additional complexity. Out-of-order messages handling can be tricky and is something you need to think of. For example, a chat message hello from stream 1 might arrive after how are you from stream 2, even though hello was sent first. This happens because different streams can have different network path or processing time. The solution is to add timestamps or sequence numbers per logical conversation, not per stream. Don't rely on arrival order to determine message order. Some streams can succeed while others can fail, which creates consistency challenges. You need to design your data to be independently meaningful or add correlation IDs so you can detect when related data gets out of sync. High-frequency streams can monopolize bandwidth and block low-frequency but critical streams. If you are sending 60 frames per second position updates constantly, they might consume all available bandwidth, causing a critical message to get delayed. The solution is to set proper stream priorities using QUIC's built-in priority mechanisms. When implementing WebTransport, you will need to make some key design decisions that don't exist with WebSockets. The fundamental question is, which data should be reliable versus unreliable? The way I think about this is to ask yourself, is all data harmful or helpful? If all data is helpful or neutral, use reliable streams. If all data is harmful or even worthless, use unreliable datagrams. Some data should always be reliable. Chat messages where users expect all messages to appear in the conversation history, configuration changes, or setting updates. Basically anything where losing the data would break the user's mental model or how the application works. Some data should always be unreliable. Live video frames where all frames create stuttering and delay. Live audio chunks where all data causes echo, delay, and synchronization problems. Sensor reading where the latest temperature or GPS position is much more valuable than reading from even a few seconds ago. Mouse movements and cursor positions where you're getting constant updates and missing a few is completely fine. For stream prioritization strategies, you need to decide what happens when bandwidth is limited. You have several approaches. Fixed priorities where critical data always gets the highest priority. Contextual priority where the priority changes based on application state. For example, during a presentation mode, the presentation stream gets highest priority, but during normal editing, users' interactions get priority. Bandwidth-based priorities, where when the network is performing well, everything gets equal priority. But when the network is poor, strict prioritization kicks in. Or you can let user choose with options like prioritize voice over video or prioritize file downloads over real-time updates. Looking ahead, the future of WebTransport is quite positive. WebTransport will continue evolving as the specification matures. The server ecosystem will mature significantly as the specifications stabilize and more developers start using it in production. WebSockets aren't going away. They will remain the default solution for general-purpose real-time applications where simplicity and universal compatibility matter more than maximum performance. Here's a quick technical comparison summary. WebSockets use TCP-based transport with single-stream multiplexing, always reliable delivery. They have the head-of-line blocking problem, and they required HTTP 1.1 or higher to upgrade HTTP connection to WebSocket connection. WebTransport uses HTTP-free and QUIC transport with multiple streams. Configurable reliability per stream, no head-of-line blocking across streams, quick 0-to-1 RTT handshake, growing browser support without Safari yet, and an emerging ecosystem. Here's my recommendation for teams. Short term in 2025. Experiment in non-critical scenarios and continue relying on WebSockets for broad compatibility. Medium term. Implement feature detection and graceful fallbacks. Use WebTransport for performance-critical applications and build team experience gradually. And long term. Adopt WebTransport where it provides clear advantages and maintain a hybrid approach for maximum compatibility. So that's my take on WebTransport. I hope this video helped clarify how it works and when you should consider using it over WebSockets. And before I go, I would really appreciate if you could hit the subscribe button. I make videos rarely but consistently, so if you subscribe, you won't miss any new content. There are no shorts or daily videos here, so you definitely won't get spammed. That's it for today. Thanks for watching, and I will see you in the next one. Bye.